Hello everyone. In this video we are going to talk about the formulation of finite element analysis for axial members, which are columns, beams, and frames. So in columns we really can consider the only loading and the only deformation to be in the axial direction. So we can consider the elements of a column to only have one DOF, 1 degree of freedom, at each node, which is along the column. And if we have enough of elements, then we can approximate the actual, basically, axial deflection, right, or the axial displacement of the nodes versus their location y. Okay, we can approximate it by a bunch of lines that are continuous, right? So they all have continuity at the common point. And the more, of course, the more elements and nodes we have, this combination of these lines is going to be closer to the actual curve. So what we can do is we say, remember, FEA is an approximation. So we say that we approximate U, which is the axial deflection, versus Y, which is the physical location of the node, to be a line like this. And this is just for one element. And then at the two nodes, I and J, on the two sides of it, where the locations of those nodes are YI and YJ, then the U's are UI and UJ. So if we plug in these two basically boundary conditions for it, we can find the constants C1 and C2 to be these ratios. And if we plug them back, then you can get what? You can get this function to be the approximation for the actual displacement. So this is that line. Now here we go ahead and call each one of these terms in parentheses, this one and this one. We give them a name and we call them S sub I and S sub J, and we call them shape functions. And we can write our U to be a simple product of U's and what? Of the S's. So U's are the nodal displacements and S's are the functions of Y, and a simple product between S and U, and if you put the S's in a vector and U's in a vector, then you can say S times U, or S transpose times U, is what? Is going to be the function U. So we write our function as the product of what? Summation of products, or like a dot product between nodal values and some functions of y, and you clearly see they are both functions of y. And again, we call these functions the shape functions, and they are clearly linear functions in this case because the function itself is linear. Now, there are a few other things that we can add about these shape functions. Is one, each shape function has a value of 1 at its own node and a value of 0 at the other node. So if you look at SI, if I plug in YI in here, right, it's going to be YJ minus YI, which is L divided by L is 1. If I plug in YJ for Y, it's going to be 0. Similarly, SJ at YI is going to be 0, and then at YJ is going to be 1. So if you want to basically plot versus y these S functions, right, and this is like 1, this is 0, this is YI, and this is YJ, one of them goes from this point to this point, the other one goes from this point to this one. And this green one is SI and the blue one is SJ. Okay, that's one thing. The other thing, you can write them based on the local frame here. So instead of the capital Y, you can write them based on the small y. If you remember from the video on the truss, then you remember that the origin of this global frame can be put anywhere. Let's say for the sake of this picture here, it can be, let's say, at the ground, so it can go up like this, and there is only one fixed frame like that. But the local ones, they start at the beginning of each node and they go up like this, right? So there is one per element, and so this is the small y. So small y only changes between 0 to L, and if we write it in terms of small y instead of capital Y, then our shape functions can be written as 1 minus y over L and simply y over L. Okay, so we can write them that way too. Now, how do we basically formulate the finite element problem for the columns? So we use the minimum potential energy formulation and the strain energy, which in the linear region is sigma times epsilon, and here sigma is E times epsilon over 2 dV. Now epsilon in this case is d of u over dy, and so u, remember, it was si ui plus sj uj, and you take derivative of these two functions with respect to what? With respect to y, and plug it in. Clearly the derivative of sj with respect to y is 1, which you can see here, 1 times that, and the derivative of, or 1 over L, of course, and that's the L over here, and the derivative of this si with respect to y is negative y over L, which you can see here, that's the negative 1, and that's L. So the whole derivative is going to be uj minus ui over L, and so that's your epsilon or strain. If you square it, then this is the square term, and this square term does not depend on, or you can assume this is constant over the volume, so you can bring it out, and then what you will have is E over 2, which you can see here, and then this L here is going to be L squared, so there is L squared, and then integral of dV is going to be volume, and volume is A times L. So 1 power of L is going to be simplified, and that's this single power of L that you see, and that's the A. Okay, so the total strain energy for a member under axial load is AE over 2L uj minus ui, the whole thing squared. And so the total potential energy is the strain energy minus the work done on the external forces. And based on this principle of minimum potential energy, the derivative of this pi with respect to each one of the ui's or uj's is going to be 0. So if we do partial with respect to ui, the result is ae over L ui minus uj equals fi. If you do it with respect to uj, it's going to be ae over L uj minus ui minus fj equals 0. And these two equations, you can write them like k times u, where u is ui and uj. This thing equals some f, where f is going to be fi and fj, and k is going to be ae over L 1, negative 1, negative 1, and 1. So this is the element stiffness matrix, and this is the element loading matrix or loading vector. So, and then as I said, if we call this ui uj, just call it u, small u, then this is the same format that we had for trusses, and we can from here, once we know the nodal loadings and the boundary conditions, we can find all the remaining u's and all the unknown reaction forces. Okay, so the formulation of the problem is pretty simple. So here, let's apply to an example. So here I have this column. It has 5 nodes and 4 elements, and these are the nodal loads: 30, 25, 25, 25,000 downward on nodes 2 to 5 or 5 to 2. Each element is 15 feet. Node 1 does not move. And the E is 29 e to the 6 or mega psi, and A is 39.7 inches squared. So using these, we can find the K for each one of the elements. Clearly, K has A, E, and L, and these 3 parameters are the same for each one of the 4 elements. A is the same, E is the same, and L is the same. And so this is going to be their stiffness matrix for each one of the elements. and then you add them together, right? So remember here we have basically U1, U2, U3, U4, and U5, and the same thing for the rows, and then we plug in each one of those matrices into its corresponding position. You see somewhere that they have overlap, you have entries added together. So this is going to be the global stiffness matrix for the whole column. Then clearly the F's at the two ending nodes are the loading matrix for that element. Therefore, if I want to calculate the nodal loads, then the nodal loads are going to be these numbers that you can see. On node 1 there is no load, on node 2 there is negative 50,000. You might say, where's 50,000? Well, there is a 25 and there is the corresponding 25 on this side. It's not just written. The same thing here, 25 and 25, 25 and 25, and here 30 and 30. So you get 50, 50, 50, 60, and this negative because they are all downwards. So these are the nodal loading, and again, you say K times U equals F, and U1 is already known, right? What about now, another thing we have to pay attention to is the force at node 1 is not really zero, okay? This is just the external load. This is not really all of the forces. At node 1, there is some force R that is coming from the ground. And here we did not count it. Really, if you want to do it, this has to be like R. Okay, and then when you apply this K times U equal F, then your U1, right, this whole first row times U equals that R. That is an equation with two unknowns, U1 and U2, and R, but U1 is 0, so the real two unknowns are R and U2. So that first equation is going to give me two unknowns, U2 and R, okay? But if you look at the other four equations, they are all involving the U's, and the right-hand sides are known. So what I can do is just consider what? Just consider this area here, which involves U2 to U5, multiply that by U2 to U5 and set it equal to what? Set it equal to this matrix. If I do that, then the only unknowns are U's, and if I solve for U2 to U5, these are the numbers that I will get, and they're all negative, and it does make sense because the forces are negative. Then I can go back and say that the reaction matrix is equal to K global times what? Times U, and then minus F. And if I do that, then the matrix of my global reactions are going to be what? You find some number at node 1, and then everywhere else you find 0, because at nodes 2, 3, 4, 5, there is no reaction, support reaction. At node 1, you'll find the number, and what is the number? Clearly, it's sum of all of these forces. So you have 350,000 and a 60,000, so it is going to be positive 21,000,000, okay? And that is the reaction there. But here, really nobody asked for that reaction. All you need is the nodal displacement. So your solution is done right here once you found the U's. Okay, that's it. And if you can see, the solutions are getting bigger and bigger as you go from U1 to U5. And that's, again, obvious because the constraint is at the bottom and the top one is free. So as you go up, your displacement should increase. Okay, so this is a simple column analysis using the loading matrix and the stiffness matrix that we found for each element. Now we can go to what? We can go to the beams. In beams, one of the definitions that we have for beam, how is a beam different than other structures? Well, the length of the beam is much larger than the dimensions in its cross section, right? So if you have a beam, then basically if it has 3 dimensions, and you might call them A, B, and L, this L is clearly way bigger than A, and it is way bigger than B, at least an order of magnitude bigger. So you can call it beam. Typically it's much bigger than that. Okay, and for beams here we assume 2 degrees of freedom at each node, 1 vertical deflection and 1 rotation. And you might say, what about the axial displacement like you had for the column? And you might say, in my solid mechanics class, when I basically studied the beam, I did plots for axial loads, I did plots for shear force, and I did plot for the bending moment. So I assume you should have an extra nodal displacement at each node in the axial direction. Yes, but in this case, we assume that your beam does not carry any horizontal load. So no horizontal force, like we do in this next example, no horizontal force is going to be applied from the supports or anywhere on the beam, okay? So we assume the beam is not exposed to any horizontal force from outside, and we neglect the elongation in the beam compared to the other dimensions. So this is an approximation here, okay? This is not like the best way to model a beam. Ideally, you have to add that extra degree of freedom, but we'll do it in the next topic, which is a frame. As we'll see when we go to the frames, then we treat them with all 3 degrees of freedom, okay? So bear up with me here. We are just going to work on 2 degrees of freedom if, again, the small horizontal displacement is negligible. So we only consider 2 DOFs. Now, in beams from solid mechanics, if you call the vertical deflection nu, the stress sigma, the strain normal strain epsilon, the bending moment m, the shear force v, and the load density omega, and rho, the radius of curvature, all of these relations apply in what? In a beam, okay? The normal stress, the strain, the moment, the load density, and the shear, and they're all related to the derivatives of basically m, v, and omega, the derivatives of nu with respect to x, okay? So we know all of this from solid mechanics, and I refer you to a solid mechanics book if you don't know about it. This is in pure bending that this happens. And now let's go ahead and look at how we formulate the beam problem. So here your element has 4 degrees of freedom. We call them UI1 and UI2, UJ1 and UJ2, where 1s are the vertical displacements and 2s are the rotations, okay? Now, since your element has 4 degrees of freedom, we can say that this vertical displacement nu as a function of x, which is the location along the beam, I can approximate it by a 3rd order polynomial which has 4 unknown coefficients. C1, C2, C3, and what? C4, right? Since I have 4 degrees of freedom and I have 4 boundary conditions, ideally I should be able to find those C's, and that's exactly what it is. So here we assume that, not assume, based on the definition of U's, then at 0, here is x of 0, and here is x of L, and x here is your basically local coordinate. Nu at 0 is ui1, and at L it's uj1. And then the derivatives of nu with respect to x, which are the angles, the angle of rotations, they are uj1 and uji2 and uj2. And you know that the angles, right? Maybe I can add something extra. Theta, the angle of the curve of the beam is d nu over what? D nu over dx. And this one you also have seen in solid mechanics. The angle of the neutral axis with respect to the horizontal axis at any location, which here we show with UI2 and UJ2. So these are my four conditions at the boundaries. That's my polynomial. If I plug in these conditions into that and try to find C's and plug them back, I can write, and I don't need to find all of them. I can, when I plug the final C's, plug them back, I can write this nu as what? As the product of the nodal values, okay, times 4 shape functions. So something very similar to what we did for the column, right, where the nodal values are multiplied by shape functions to approximate your actual function. We do the exact same thing for beams, but here we have 4 nodal values and 4 shape functions, SI1, SI2, SJ1, and SJ2, and these are these functions which are coming from those constants C1 to C4 and the combination of them with the length of the beam and the X position. So this is what this is going to be, basically my vertical deflection of the beam at any point. It's vector S, which are functions of X times what times U, and clearly in this case it is a nonlinear function because in the beginning we already considered it nonlinear. Okay, again, the finding the stiffness matrix and the loading is done using minimum potential energy. So it's the exact same thing. We use a strain energy, and this time your epsilon is gonna be negative y d squared v over dx squared, and this is coming from here. Okay, or negative y over rho, where rho, the radius of curvature, is basically 1 over the second derivative of the vertical deflection, rho, the radius of curvature. Okay, so we plug that in, and here this integral of dv, I'm gonna separate it into integral over x and integral over a, and this term y squared and the second derivative squared I separated. So I write my integral as the product of two integrals, where this term here is clearly the moment of inertia I, e over 2 is there, and so what we need to calculate is this integral here. If I calculate this integral, second derivative of nu with respect to x, square it, integrate it, that should give me the strain energy. Now, how do I do that? Well, remember, nu was S times U, and S had 4 components. These 4 components here, right? And each one of them is a function of what? Is a function of X. So what I need is, now take second derivative of what? Take second derivative of these S functions with respect to X, because U's are just constant numbers. So what I need is take second derivatives of these S's, and here I call them d's. So these are the second derivatives of these functions, right? Just look at the first one. What is the derivative of this function with respect to x? Well, clearly it's what? It's basically negative 6x over L squared, right? And this one is basically 12x over L cubed, and that's exactly this guy here. And then SI2 is going to be this one, SJ1 is going to be this one, and SJ2 second derivative is this. So we call these functions of second derivatives, we call them d. And so the second derivative of nu with respect to x, I write it as du. So what I need to do here is to plug the du and square it. And since these are matrices, in order to square them, I multiply transpose of it by itself. So this is transpose of d times u. I multiplied by du, that is like du squared. And so I need to carry this integration here, where u's are constants, D transpose D is the function of X that you need to integrate, right? And I can do that one. The other thing is the work done on the external forces is the summation of FU, where F are the nodal forces and U are the nodal displacements. So this is the total potential energy, which should be minimum with respect to the displacements, the nodal displacements. So I take derivative, set it equal to 0. And if I do that, then the derivative of this guy here, the derivative of this with respect to UK, when I carry all the integrations and then take the derivative with respect to UK, is going to be what? Is going to be this one here, right? So the stiffness matrix is going to be this portion, which you can see over here, right? And then for this second term here, I can either do something similar or I do it here in a different method, using a different method to find the second term. So the first term I found, that's the first term. The second term, I'll show you how to find it. From there, I can find the nodal loading. From the first term, you always find what? The element stiffness matrix. From the second term, you find the element loading matrix. Okay, now let me show you how to carry out the second term, how to do the second term. For the second term, what I do, I look at the reactions of the two sides of an element, and from there I can find what? I can find basically the forces. Or you might say, no, I really want to carry the first one the same way that I did the second one. I did the same as I did the first one. You can do that. This summation of the work done on the nodal forces is equal to what? Integral over the length of the elements of the load density times the vertical displacement times the small increment in length, right? And you might say, where does this come from? Well, here is your beam, and it is under this constant load with density omega. And so what I can do is I can look at the small portion of this where the length is dx, and this guy at the location x, it goes down by a distance of nu. So the load corresponding to that distribution at that location over that dx, the load here is going to be what? Of course, it's going to be omega dx. So this is the force that you basically apply, and it goes down by that displacement. So the force times displacement is the work. But that's a small work, so you integrate it over the whole length to get the total work. And that's where this whole thing comes from. Okay, so if you're wondering where that terms come from, that's the explanation. We can do it that way. And then the problem is this nu, we have to plug this function back for it, this guy here, and integrate it over the whole length and look at all different scenarios for omega. Sometimes omega is really constant. Sometimes omega is linearly increasing. Sometimes there is no omega. There is only a concentrated force or something. Under each one of them, you find the integrals. You find the whole work. Take the derivative of that with respect to what? These basically individual u's, and then find the nodal loading. That's one way to do it, but as I said, instead of that, what you'll do is you look at one element and look at different scenarios. First scenario is the uniform loading, density omega and length L. And what you would do is you look at the equivalent of this system, which would be basically only applying the loads at the nodes. Now, why only at the nodes? Because that's what we want. Remember, what we want is the loads at the nodes, right? Because all of these U's are happening at the nodes, nowhere else. Remember that? these U's are happening at the nodes. So if I find which force and which bending moment are acting on these U's, those are exactly equivalent to what? To this whole term here. Because derivative of FU with respect to U is really F, right? That's all it is. But since the U's are at the nodes, the F should only be at the nodes. And in this case, the omega is not at the node. It's all over the element. So I use the equivalent of that only on the nodes. And then clearly these WL over 2's, which are forces, and in the vertical direction, they would work on what? They would work on UI1 and UJ1, which are vertical displacements, and then UJ2 and UI2 are the displacement due to what? Due to these bending moments, WL squared over 2, and the same thing on this side. Therefore, I can use those four guys and say that the nodal forcing matrix for this scenario is exactly this guy. Look at it. Right? This is for what? This is for UI1, for the vertical displacement 1. This is for what? This is for UJ1, the vertical displacement on node J. This is for what? UI2, rotation at node I, and this is for what? UJ2. And you see these three are negatives, that one is positive, and that comes from the direction. Right here, counterclockwise positive, clockwise negative, and downwards are also what? Negative. That's why you get those three negatives here. So under this kind of loading, this is the nodal loading matrix that you have. Now, if it becomes linearly increasing loading, then again, from solid mechanics or statics, you can find what? Or both of them actually. You can find the equivalent, again, vertical forces and bending moments. And again, you can form the equivalent nodal loading. And then if it's concentrated force, again, you can find the equivalent system and find the nodal loading. So one of these three scenarios, depending on how the loading is, you're going to use one of these three is going to be your nodal loading, and this guy is going to be your what? Is going to be your stiffness matrix for that element. So now that we know the stiffness matrix and the load, let's look at an example. So here we have a beam, and this beam has a fixed support at node 1, and then it has a roller at node 2, and then from 2 to 3 is an overhang. And the density of the load is constant at 25,000 newtons per meter. The dimensions are given. What you need to find is the vertical displacement at node 3 and the rotations at node 1 and 2. The E for the beam is given, the I for the cross section is given, the loading is given, and you also want to find the reaction of the supports, right? In this case, how many reactions do you have? Well, we have three reactions here, one vertical, one horizontal, and one what? Bending. And here you have another vertical. Now, clearly, in this case, the horizontal is 0. As I told you, we assume that the beam has no horizontal. So this guy is going to literally be 0. What we need to find are these three reactions, but guess what? We only have two equations. One is some Fy equals 0, one is some moment about, let's say, 0.1 is 0. So this beam is clearly statically indeterminate. But remember, I told you that FEA can solve statically indeterminate problems and find the reactions for them. So let's go ahead and see how. So how many elements do I need here? 2, only 2, right? This is element 1 between node 1 and 2, and then this is element 2 between nodes 2 and 3. And you might say, why didn't you use more nodes and elements? Well, I don't need it. Why? Because between 1 and 2, everything is the same. Between 2 and 3, everything is the same. So I really do not need to use more basically elements and nodes here. So how do I attack this problem? Well, I look at element 1. For element 1, remember K is what? K is EI over L cubed, and then these numbers, 12, 6L, and so on. So what you really need is L, E, and I. right? And you have everything for that. You have the E for it, you have the I for it, and you have the L for it. L is 5. So if you plug them into that formula, this is going to be what? K for element 1. And this is for which displacements? For UI1 or U11, because here and you call this node 1. U11, U12, U21, and U22, where the first subscript is the node and the second one is that degree of freedom. 1 means vertical displacement, 2 means rotation. Okay, so this is your element 1. What about element 2? Again, everything is the same. We have E, we have I. The only different thing is this guy, 2.5 L. So if you calculate it, this is going to be K of 2. And again, the displacements are for nodes 2 and 3. And now you add these two K's together, and you're going to get a 6 by 6 here. Why 6 by 6? Because I have 6 total displacements, right? I have 3 nodes. Each node has 2 displacements. So these guys are going to be U11, U12, U21, U22, U31, and U32. And you combine these two, as I showed you in the past, and you get this 6 by 6 K G. Okay, clearly you're gonna have a lot of overlap. Which areas have overlap? Areas of node 2. So you are going to get basically a lot of overlap in this middle area here. Let me show you in this area, because let's see here. This is shared by both of these 4x4s. So here in this area here, that's the sum of the numbers in here and in here. If you add these numbers together, you get the numbers in that red region. Okay, the rest of the numbers are from the original matrices. Now, which condition do I have here for the nodal loading matrices? The condition is uniform. Omega is uniform here. So I'm going to use this matrix here. I'm going to use this top one because this is for uniform loading. So I'm going to use this one. And all I need is omega and L. So here I'm going to go and get that, but L's for the elements are different. One is 5, one is 2.5. So I get F1 and I get F2, and then again I add them together and I get again a 6 by 1, and again the area of overlap is this area in the middle. Here this is some of the numbers from here and here. Everything else is going to stay the same. Now we say K times U equals F, and which U's do we know anything about? Well, if you look at node 1, what do we have at node 1? Node 1 is not going to move, so U11 is the same as, and it's not going to rotate, it's the same as U12 equals 0. 2 boundary conditions, and then here at the roller, you have what? You have U21 equals 0. At roller, you don't move up and down, but you can rotate. So U11, U12, and U21, the first 3 are all 0. These 3 guys, they are all 0. So all we need is the bottom 3. So all we need is really the bottom portion of the K and the bottom portion of the F, and this is exactly that part. And if you solve for the 3 U's, these are the 3 U's that you'll find. Now pay attention to the units. This is U22, it's in rotation. The unit is in radians. The same for U32, which is a rotation. But U31, which is a vertical displacement, the unit is in meters. So pay attention very carefully. Finally, we go to the reactions. Reactions is always equal to K times U minus F. And here I plug the whole U back, I plug the whole K back, and the whole F back. And there are 3, of course, reactions here. What are they? They are R1, M1, and R2. M2, R3, and M3 are 0. Why? Because as I said, at the roller, there is nothing to stop rotation. So moment at node 2 equals what? 0. And then in a free end, both the rotation and the force are going to be 0. Right? That's a free end. So all we need, as I said, is basically, this is a moment. It's going to be this way. Right? So these three are 0 because of the boundary conditions. At node 1, we have a vertical reaction and a moment. At node 2, we only have a vertical reaction. And these are these three guys, which you can get from here. And you see, although the beam was statically indeterminate, I could easily get all three of them. Now, does this make any sense? You can check. For example, you can add these two numbers together, add these two, and see how much you would get, and then compare it against the total vertical load, which is what? Which is 25,000 times 5 plus 2.5, right? So if you compare that against what? 7.5 times 25,000. See if the numbers will match, right? So this is going to be something like 180 something thousand, right? And if you add this 54,000 and 132, you see that's again 180 something thousand. So you see they match. If they don't, there is definitely something that you did wrong in your calculations. So always when you get your numbers, do a sanity check. And look at the signs of these. All three, they have negative signs. Does it make sense? Yes. It says node 3 is going to go down and the rotations are negative. Does that make sense? So if you look at this beam, what's going to happen as a result of this force here, right? So if I want to draw the beam after applying the force, probably the beam is going to be something like this, right? Where, and this is, let's say this is the original one. Let's say this is, let me draw the original one. So this is the original one, and this is that, and this is this. Here you have nothing, it goes up to 0 and then it goes down. So it's gonna go like this probably. Something like that. And clearly at node 3, you definitely have a negative deflection, and then you will have a negative rotation as well, right? You can see here, and clearly this is a negative rotation, as you can see. Okay, so always do a sanity check. Last part. I know this video is getting long, but I want to finish up all axial members in this video. The last part is a frame. And frame is basically the one that has 3 DOFs at each node. So you have an axial displacement, a vertical displacement, and a rotation. And you give them the names by 1, 2, and 3. Use 1, 2, and 3. And in general, a frame member can have angle theta, because it's just like a truss, right? Where the ends are bolted or welded or anything like that, or a beam that has horizontal forces applied to it. In all those cases, you're going to apply the frame formulation. And we have a global coordinate frame and we have a local coordinate frame, just like a truss in general, because the members can have angle. And if you want to go from local members to global members or vice versa, you can use what? You can use a transformation matrix, right? And this transformation matrix is literally a rotation z with angle, in this case, negative theta. Why negative? Because I'm going from U capital to U small. In the past, we had this in the trusses, and that T had this negative and that positive, or angle negative theta. In this case, I'm doing the opposite. So this T here, this T, is the same as T inverse that I had in the truss formulation. Okay, here I'm going from the global displacement to small ones, to the local ones, not the other way around like in trusses. So don't think that my formulations are contradicting each other. It's not. So you have two blocks of rotation Z and then two blocks of 0, of course, because the displacements of one node has no effect on the displacements of the other nodes. Okay, so that's the transformation that you need from global to local. Now, locally, how do you get your stiffness matrix? Well, here I don't need to do the minimum potential energy formulation one more time. Why? Because this guy is equivalent to what? This is equivalent to the beam that we already formulated. Remember that? Plus what? Plus the column that we also formulated. Remember, I had a K and F for what? For beam, I had a K and F for what? For the column. And this is exactly the summation of the two. So here, all I need to do is to go and get what? The stiffness matrix from the columns, the stiffness matrix from the beams, and add them together. Now you might say, where do you get all these zeros from? Well, remember, in beams, all you have are these four. You go the columns. If you go back and look at the columns, right? Look at it here. All you have is what? AE over L, negative A over L, negative A over L, and A over L. That's all you have. So what happens to all of these zeros here? Well, they are for those degrees of freedom that the column doesn't have. Remember, what do you have here? Well, this is what? This is UI1. This is UI2. This is UI3. This is UJ1, UJ2, UJ3. Well, guess what? All your beam does have is UJ1 and what? UJ2. There is nothing else in your column. So let me write it here. The 2's and the 3's are not here. So that's what we call them, right? Because I don't have the vertical displacement and the rotation for a column, then I use a bunch of zeros for them. And on the other hand, for a beam, since I don't have what? I don't have the ones, then I use what? I use these zeros for the ones. Okay? And here as well, and here. Why? Because this guy here is what? UI1, this is UJ1, and then if you look at the rows, what do you have here? This is UI1, and this guy here is UJ1. So at those intersections, you have all of these zeros, and all of these 12L, 6L, and everything, they are all coming from what? Of course, they are all coming from this guy over there. So you put them together and finally you get this big local stiffness matrix. Now this is in the local system. Remember, we solve in the global coordinates. So I need to take my local frame to the global frame, and what I need to do is to use T transpose T from the left and the right side to take it to global frame. This in linear algebra, we call this product, we call it similarity transform. Okay, if you want to move a matrix from one frame to another, we call it the similarity transform, and the T matrix is exactly what is provided here. Now, if you want to carry that, it is going to get you similar 6 by 6 matrix, but it's going to be way more complicated. So here I didn't do it, and you can do it using MATLAB Symbolic if you want to get some nice formulas for it, but it's going to be a little bit big messy. Okay, but you can always do that using this formula. What about the loads? Well, the load is simply, again, summation of the loads of the beam and the column. So these portions, these two are coming from what? From the beams, and these two. These are from the beams under constant omega. It's this top guy here. And what about these zeros? Where are these zeros coming from? Well, here we assume that there is no axial force on the frame. If on the frame at any node there is an axial force, you have to fill those and not leave them zero. So it's useful for a frame like this, in this example, that you see that at nodes 1, 2, and 3, there is no horizontal force. Now, if I come here and plug in some force like that, right, which is aligned the member 1, 2 here, then I would add that for the end node of member what? Member 1. Okay, so here we assume that there is no axial force on it, and the distribution is the uniform distribution. If it's not uniform, then we can use these other ones. Okay, we can use either this one or this one. So we just need to combine together. And as the last part here, let's look at this example. So here I have a frame, and in this frame, it's clearly a frame because the load is not applied on the nodes. Okay, and here I have a rigid connection, so clearly this L-shaped member or inverse L-shaped member is definitely a frame. The cross section and the eyes for each section is given for elements 1 and 2. I only use 3 nodes and 2 elements. W on 1, or omega on 1, is 800. The omega on the other one is 0. This other one has no load on it. And what are the angles? Well, clearly for member 1, 2, the angle is 0 degrees. And for this member, the angle is what? If you look, it goes from 2 to 3. The angle is basically 270 degrees. And you need them to plug them into the T matrix, okay, which needs theta. So if we do that and calculate this local K and then transpose of T left multiplied, the T itself right multiplied, you get the global Ks for elements 1 and 2. Now for element 1, the global and the local are the same. Why? Because theta is what? 0. So once you calculate the local, no need to pre and post multiply by T transpose and T, because T is going to be what? An identity matrix, basically. T is going to be an identity matrix in this case for element 1. For element 2, T is not going to be identity matrix. So the K local and the K global are not exactly similar, as you can see. Then you join them together and you get your 9 by 9 global matrix for the entire frame. Okay. Now for the loading matrices, for element 1, since there is no horizontal force and the loading is basically uniform, we're going to use this formula here, right, that we learned already. And except for the zeros that we add, so it is going to be basically this guy here, and we have the numbers, right? For the omega L over 2 and omega L squared over 12, we get the numbers. For element 2, there is no loading. Element 2 is completely what? Completely free. There is nothing on it. So for element 2, it is going to be a bunch of what? A bunch of zeros. And then we can add them together. So your total F global, which is F1 plus F2, is going to be a 9 by 1 matrix or vector where it is going to be 0, negative 4,000, negative 80,000, and then 0 and negative 4,000 and positive 80,000, and then 3 zeros. And now we need to look at the boundary conditions here. At node 1 and node 3, they are completely fixed, so all 3 degrees of freedom are 0. So u11 equals u12 equals u13 equals 0. Similarly, u31 equals u32 equals u33 equals 0. And node 2 is completely free to move in all directions and rotate. So what we really need is only the elements of 2. Therefore, we really need the middle portion of the K, which is for the 2's, U2, 1, 2, 2, and 2, 3, and that is this area here. From the K, and then this area from the F. And that's what you see here. If you solve for it, you can get the 3 U's, U21, U22, and U323. And again, you see the 21 and 22, the horizontal and vertical or axial and transverse displacements are in inches, and the rotation is in radians. So here we can exactly determine how the beam is moving, and you see it's moving in negative X and negative Y direction. So if it's the original one, the next one, this guy is going to go negative X and negative Y, right? And this one is going to stay the same. And this one is going to bend like this, okay? And this is how your beam is going to look like in negative and negative numbers. Okay, so I guess I told you what you need to know about frames, about beams, and about columns, all of the axial members, and you learn about the shape functions and the formulation of them. Hopefully this video was useful to you. I will see you in my next lecture.